Live started, sir. I think you are in mute. Sir, I think your mic is mute.
Will we wait for students to join or we'll start?
I think, yeah, I think you can start, sir. Only one student join.
Okay.
Jayanta Shah.
Yeah.
Okay, sir, thank you.
Okay. So, Jayanta, do you have any questions that you want to answer, that you would like to ask?
No, I don't have any questions right now.
Okay. Okay. There are some questions that were asked in the discussion forum this week, and we said that we will just quickly discuss that. Are you guys able to hear me? Yeah. Am I audible, guys?
Yes, sir.
Okay. So there was a question regarding why can't we do read in SRAM with the bit lines pre-charged to 0. So let us just quickly look at that question while people join, and that will give us some recap of what we had studied in SRAM as well. So let's just quickly review the read operation of the SRAM to answer this question. So the objective of a read operation in SRAM, through what we saw in this particular schematic, is that your node N1 had a value 0 stored in it, and N2 had, of course, the complementary, which is 1 stored in it. And the idea was, how will the read happen? And as we saw, first we pre-charge the bit lines to VDD, and both the bit line and bit line bar are pre-charged to VDD. And then what you do is, after that, you assert the word line. And as a result, what happens is the pass gate 1 transistor turns on. The first part of the analysis involved why the right-hand side of the branch, which I'm indicating over here, the PD2, PU2, PG2, all of this will not really function. All of this will not function because PG2 transistor is off. This is because if you look at the source, drain, and gate of the PG2 transistor, all nodes are at VDD. Since all nodes are at VDD, there cannot be any effective turn on condition and no current will flow through it. So through this, we realize that nothing will happen at the storage node where 1 is stored. So then we shifted our gaze towards the storage node N1 where 0 was stored. And there we realized that the bit line is VDD, your pass gate transistor has been turned on, and therefore there will be a finite read current which will flow from pass gate to pull down transistor. And by doing this extensive analysis, we saw this read current will flow. And as a result, whenever a current flows, it is obvious that if current flows through any node, there has to be a drop in potential. And we saw that the node, which was earlier at 0, will shift to 0 plus delta V dash. And this 0 plus delta V dash is your disturbance in your internal storage node. And you had to be very careful about designing the cell ratio of the transistor of the SRAM cell. The cell ratio was the strength of the pull down transistor versus the strength of the pass gate transistor. And you had to ensure that the strength of the pull down transistor should be much larger than that of the pass gate transistor. Why do you ensure that? Because as you can see in this diagram, you would want this particular node to be as close as possible to 0, because you want this disturbance delta V dash to be as minimal as possible. So it's very simple. There is a tug of war which is happening at this internal storage node between the two guys who are pulling in different directions are the pass gate transistor and the pull down transistor. And if you want it to be closer to what the other end of the pass gate transistor is, which is 0, and that's what the objective is, you would prefer that the pull down transistor be made much smaller than pass gate transistor. And that is why we were able to facilitate, as you know, non-destructive read. But the question which was asked here is what will happen if the bit line and bitline bar are precharged to 0. And there you can understand everything will flip. And if you think a little bit carefully, I thought I'll discuss this in detail because a lot of things will change. And there is a fundamental reason why this may or may not work. So let us analyze very carefully with the same diagram. So the suggestion made by one of our participants is what happens when bitline and bitline bar, instead of being pre-charged to VDD, are now, well, you can't really call pre-charge. All the charge is removed such that both bitline and bitline bar is 0. So first, before we discuss what happens, let's even consider the practical implementation. What does it even mean to charge a value to, let's say, bitline or a very big, as we know, bitline and bitline bar are these large capacitive line. They are these big lines which have a sizable capacitance. We also realize that the internal storage node capacitance is very tiny compared to what you see in this large bitline and bitline bar. But what does it mean to precharge something to 0? It simply means that you have to remove whatever residual charge that there is. And that itself can sometimes be a very lengthy process because you are trying to, from the end, how the pre-charging happens. It happens to 3 NMOS gates. And now you'll have to change the architecture of the NMOS, of the PMOS pre-charge circuitry also. You have to start making it NMOS. So a lot of things have to change. But so that gives you some overhead. But why doesn't it fundamentally work is what we would like to discuss here. So suppose you pre-charge bitline and bitline bar to even 0. You see, now if bitline and bitline bar are pre-charged to 0, everything, the read operation should ideally flip. What I mean is, earlier, as we had just discussed, the read current flows through, as you can see, the storage node N1, where the internal node was stored to 0. But that cannot happen anymore because this bit line has become 0. This PG1 transistor will not be operational. So the read current cannot flow through PG1 and PD1. Okay, so you have to look at the other side of the branch now. You have to start looking at what happens at PG2. And indeed, if you have PG2 and the expectation is now, instead of the read current flowing in from bitline bar inside the pass gate transistor into the PD2, what will essentially happen is there will be a opposite current will flow in the opposite direction. There will be a charging of the bitline bar. And that will create all kinds of problems. Why will it create all kinds of problems? Remember, we discussed the cell ratio. The cell ratio was ensured such that the disturbance on this internal storage node should not become too much. So here what will happen is, as your storage node 2 starts discharging through a read current, what will essentially happen? This 1 will become 1 minus delta something. But where is the cell ratio to prevent the opposite from happening? If you just allow it to discharge, it will just continuously discharge and it will flip the value. And that is not useful because it will be a destructive read process. So what do you need to do? Now, imaginary cell ratio has to be manufactured such that the pull-up 2 transistor has to be much smaller than pass gate 2 transistor. Why? Because you are trying to maintain the value of the storage node 2 to 1. And what is connected to 1? It is connected through the pull-up 2 transistor. So now you have to start making a different cell ratio. If you change the biasing scheme of bitline and bitline bar, you have to make sure pull-up 2 transistor should be stronger than pass gate 2 transistor. Can you think what could be a problem if you start trying to make the pull-up 2 transistor much stronger than pass gate 2 transistor? The problem is it completely conflicts with your pull ratio requirements. Remember, your pull ratio requirements said that your pass gate 2 transistor should be stronger than pull up 2 transistor. But now, to maintain the cell ratio with this new biasing scheme, you're saying pull up 2 should be stronger than pass gate 2 transistor, and that cannot work. And that is why principally, fundamentally, you cannot have bitline and bitline bar pre-charged to 0 for facilitating read. I hope this makes sense. Only, yeah. So before we go to any other question from online, I think, does anybody here have a question which you would like to ask? Arjun, do you have a question that you want to ask? Or? Okay, so I think one more question which was asked this week does not pertain to, before we go to RRAMs, there was one more very interesting question asked on the forum, and that was regarding the NAND flash program operation. So the question that was asked, let me go to the relevant slide and then probably I'll read out the question. This question also was very interesting, and I thought maybe we can spend some time on that. So one of the questions which was asked over here was about the inhibit voltage. So one of the questions which was mentioned is that, so I think he is referring to this particular slide where we are trying to do program in the NAND flash array. And when we were doing the program in the NAND flash array, first and foremost, we assumed that all the cells are initially erased. And in this page of our interest, page is nothing but all the cells which are connected by a common word line. We know that in both program and read operation and NAND flash happens at the level of a single word line or a single page. And the question was, suppose we have this particular string and all of them are erased. And the idea is I want to just program out of these 3 strings. Remember, string is defined as any array of cells which have a common bit line. So here, what we were trying to do is we were trying to do programming of this particular cell. And we saw that in order to do programming of only one cell is a relatively challenging affair when it comes to NAND flash because of its serial architecture. This is because you should recognize that this particular cell is in connection, has a lot of connections. So for example, in series, it is connected through many other cells which are connected by the common bit line. So we have to be careful. What do we apply on the other cells such that the other cells do not get programmed? Also, you have to recognize that the cell which we want to program is also sharing the common word line with many other cells in the same page. But as we discussed, our intention is not to program, for example, this particular cell and this particular cell. So how do you meet these competing requirements? See, these problems were not there in random access. There are no problems in random access because in random access, unlike serial access, which is in the case of NAND flash, you had individual access to all the cells. But here you do not really have individual access. So how do you manage these things? So as we saw that this is managed through this really complicated biasing schematic, which ensured that you should be able to only program this particular cell. So how was that done? First thing to recognize is that what happens to these normal transistors. Remember, right at the top of the string, the first transistors, which I have marked out in blue color and I'm indicating over here. Krupakar, you're able to see the here, right? My pointer. Okay. So if you see these particular transistors, they were called the source select line transistors. They are not flash cells. Flash cells are indicated by these two lines at the gate stack, which indicates it's a modified gate stack of a transistor. If you look at these blue lines or blue transistors, they are normal logic transistors right at the beginning of the string, and which connects it to the bit line, and right at the end of the string is also what is connected. This is also a normal transistor, which, as you know, is called GSL, or the ground select line. So first thing what you intelligently do is you make sure that the source select line is turned on by applying 10 volts. So the source select line is turned on and the ground select line is turned off. This is a very smart decision that you take. This is to facilitate two very important things. And this is where the answer to the question comes from. How are you stopping inhibit from happening? The answer is lying in how you are turning on the source select line and transistor, and how you're turning off the ground select line transistor. Now remember, this is one whole string. The idea is that if you turn on this particular transistor, whatever is the voltage that you apply on the bit line will at least appear on the first part of the string, right? That is the idea of turning this transistor on. The idea of turning this fellow, which is a ground select line transistor, off, is also very intelligent. Basically, what you are trying to do is you are trying to make this particular terminal go to float condition. And if this terminal goes to float condition, what will happen if this is on and this is off? That means there cannot be any string current. And this is very carefully designed, that you do not want any string current to flow through this string. Why? Because during program, you want all the action to happen across the gate stack, not through the source and drain. You don't want any current to flow through the source and drain. All the program or erase you want to have only in this particular direction, from the control gate to the channel. This is where you want all the potential to drop. As a result, what happens is there is no string current, but whatever voltage you apply over here, because this is a floating wire. Just imagine you have a wire. Here you apply 10 volts, here you apply float. What will happen to this wire? All throughout, since there is no current, there will be no potential drop. So here there is no current, there is no string current, no potential drop around the string current. So whatever voltage you apply at the bit line, which is the inhibit voltage, will appear across all the cells in the string. So this is the very intelligent thing that you do. And how does that help? That helps because you are artificially trying to increase the channel potential. See, the channel potential in all the strings where you do not want program to happen is artificially raised. So if the channel potential is raised artificially to 8 volts, what will happen? So if this is 8 volts over here and this is 20 volts, the potential difference is only 12 volts. And therefore, it is not enough for Fowler-Nordheim tunneling to take place. And therefore, you prevent through this inhibit voltage any kind of Fowler-Nordheim tunneling, and therefore any kind of program operation to happen for these particular cells. Whereas the cell that you want to program, you apply 0 volts. So now across this, the potential difference is 20 volts, and easily you will be able to do a program operation. So this is basically what is happening during the program operation. Yeah. So when you apply 20 volts here, you will be able to attract electrons, or electrons will do a tunneling from your channel into the channel substrate into your charge trapping layer. So this was the answer to the question. So by applying an inhibit voltage, you are able to make sure the channel potential for all these strings, all the flash cells in the string, the channel potential is raised to 8 volts. Okay. So that is the answer to the question. So does anybody from the online audience have a question? Does anybody from the online audience have a question? Okay, so another question which was asked was actually for the, if I'm not mistaken, for in the RRAM section. So the question that was asked in the RRAM section was by Raghu, and he asked, I'm not able to understand which timestamp is he mentioning at, because the timestamp goes to the last second. Is this in terms of magnitude or polarity? Because if the polarity is the same, then how other state will be formed? Are you able to understand the question?
Reset operation.
Huh.
I think he's referring to the how set voltage and reset voltage affects the LRS to HRS transition.
Which one? That's what, because there is the CBRAM and VCRAM and many are there, right? Which one is he referring to? He doesn't mention that. And the timestamp which he is mentioning is, or maybe it is 19 minutes and 27 seconds, if I'm not mistaken, because that's what I see over here. Okay. 19 minutes and 27 seconds. Okay. So I think it is this. I think he's mentioning this slide. Okay. I think he wants to ask about this. I'm presuming. Is Raghu around? No. Okay. So the question which I think he's trying to ask is from this slide, where he's saying what are the rationale for having these opposite polarity. So as we know, overall RRAMs are classified into two main parts or two main subclasses. These subclasses depend on what is the nature of the conductive filament which has formed. One is your valence change RAMs, which we are going to discuss now, and another is your conductive bridge RAMs. In valence change RAM, the nature of the conductive filament comes from substoichiometric metal oxide. So as we know, metal oxides are generally insulating in nature, but when there is a substoichiometry, basically you remove oxygen. So the resultant filament is basically conductive in nature. So this conductive filament, the formation of this conductive filament is to be looked at very carefully. And this conductive filament, when the question is for VCRAM, in VCRAM, there are two further subdivisions if the conductive filament is consisting of substoichiometric oxide. This subdivision is electrochemical and thermochemical. What is the basis of this subdivision? The basis of this subdivision is how is this created filament going to get annihilated? So how is there a breakage in the filament? And that's what we discussed. We discussed there is electrochemical and there is thermochemical. First, let's see what is electrochemical. In electrochemical, what happens is, let's assume the bottom electrode is grounded and the set was done with a positive bias. What happened in set? If you see a few slides above, you will see during the set, what essentially happens is, yeah, this is where this explains forming a set. So what happens is a lot of these, when you apply a positive bias, some of the oxygen atoms are ripped off from the lattice of the metal oxide. And these oxygen ions come and sit on the top electrode, as you can see over here. These are green oxygen anions. And what remains is the oxygen vacancies. And these oxygen vacancies in a metal oxide film is what causes the filament. Now, how does the annihilation of this filament happen? So this is how the filament gets created. Now, the annihilation of the filament, as you can see, can happen in two ways. One is your electrochemical process. In the electrochemical process, what you do, See, this was your initial state after set. So a positive set bias pulled electrons or pulled anions from these filaments into this top electrode. Now, the simpler idea is to push them back. If you want to annihilate the filament, the idea is just push them back. So if you push them back, what you essentially have to do is you have to apply a negative reset voltage. That is common sense, because if you apply positive reset voltage, the further the anions will move in this particular direction, in the direction of the top electrode. But if you apply negative reset voltage, that will give these oxygen anions some push to go inside the solid electrolyte or the metal oxide. And by the virtue that the least energy will be that they will go and again recombine with their original sites, the idea will be that this filament will get repaired. So some of the oxygen anions, by the virtue that you have applied negative reset voltage, will be pushed away electrochemically by the virtue of electric field and will go and repair this filament. So that is how your electrochemical process take place. But that's not the only way of having the transition from low resistance state back to high resistance state. That's not the only way how a filament gets repaired. There is another method, and that is called thermochemical method, which is induced by Joule heating. That simply means that even in the absence of a negative reset voltage, even if you apply a positive reset voltage, or in fact you apply any reset voltage, what you essentially do is this filament is now in low resistive state. That means a low resistive state filament will conduct a lot of electricity. So if it has a lot of current, so if you start increasing the reset voltage and you remove the compliance, a lot of current will flow through this particular conductive filament. So as we know, if there is through any, this is how even fuses work. The old fuses that we used to have in our homes, there was a filament and it was designed using an alloy, which after significant current, a surge of current flows through it, it just simply melts. So simply, that's exactly what is happening. That also used to happen through Joule heating. So the alloy was designed such that the temperature increase in that alloy makes the filament break. And that's exactly what is happening over here also. Surge of current, by the virtue that you remove the compliance current, will cause a lot of Joule heating. And as a result, what will happen is your oxygen anions can come from neighboring sites also and start filling up this deficient areas. And as a result, you will have a repaired filament. So these are inherently completely different processes, whereas electrochemical is induced by electric fields which are opposite to set. Thermochemical is induced by Joule heating, which is I into V. So if something is induced with Joule heating, the idea is if something has Joule heating, whether in this current filament, if you take any filament also, if you take any metal also, Joule heating is irrespective of the direction of flow of current, right? It's just I squared R. So if it is irrespective of direction of flow current, it does not matter whether you apply a positive reset voltage or a negative reset voltage. And that is what is mentioned by this modulus of reset voltage. That simply means it is polarity agnostic, the meaning of polarity agnostic for thermochemical. And this is how you recognize that something is a thermochemical memory, that you can set it in one particular polarity, but you can reset in either polarities. But in thermochemical, if you set it in positive polarity, you have to reset only negative polarity. Or in other words, when you fabricate a device, you set the device in positive polarity and you see that it is only resetting in negative polarity, then you're sure, more or less sure, that this is a electrochemical memory. Whereas if it resets in either polarity, it's a thermochemical memory. I hope this answers the question. Yes, Krupakar? Yes. Any other questions? So one more question is about confusion of compliance current and complete dielectric breakdown. But I think not the, and it was asked in the context of this particular slide. But I think to understand that, we can probably go back a few slides earlier. And this is where we had explained a very important concept in RRAMs. In RRAMs, it is very important to create a controlled filament. And that is the idea of the so-called forming step. Now, we must recognize that the same metal insulator, metal kind of device stack or device structure is a very universal structure. It can be used for a lot of applications. As you can understand, this is also a capacitor. Capacitor also consists of MIM only. Not only that, permanent fuses that we used in your technology such as programmable read-only memory also consist of MIM structures. There, what you do is you create a permanent filament. How do you create permanent filaments? You do a permanent dielectric breakdown. But as you know, these are not read-only memories. They are random access memories. They are resistive random access memories. That means that the filament which is created has to be turned on and off, or created and annihilated. You have to do many cycles. It has to have a very high degree of endurance, up to 10 to the power of 12 cycles even, or 10 to the power of 10 cycles. So you have to make sure that the initial filament that you create from this fabricated device or virgin device, it has to be a very controlled filament. So how do you create a controlled filament? The idea is by controlling the current that is used in the forming step. So how the forming step is done is what is indicated over here. So in x-axis, you have your applied voltage, and your y-axis, you have current in the log scale. So in what you do is essentially you start ramping up the voltage, and as you see, the electric field initially will the device will initially resist electric field. I mean, there will be very little current, as you can see from black. There will be very little current in the device. Why will there be very little current in the device? Because this is an insulator. But as we know that even an insulator has a finite bond strength or finite dielectric strength. Once it reaches a particular critical electric field, what will happen? The bonds will start dissociating. Of course, the bond energies are very high. For SiO2 or something, it is a 9 eV or whatever it is. But there is still a finite limit to it. I mean, it's not infinite. So once you start applying small electric field, just imagine these are the molecules in your dielectric. You have your positive ion core and you have your negative anions. So you have a positive cation. Let's assume it's metal, and you have your anion, which is oxygen. And once you apply an electric field in this, probably from right to left, what will happen? There will be a separation, and this separation will start increasing as you crank up the electric field. And that at a critical electric field, this bond strength will start giving way. It will start breaking. And this is what is shown through these oxygen anions being ripped out from the metal oxides lattice structure. Then what will happen is you will start seeing a sudden shoot up of current. And it is very important. And this is called soft dielectric breakdown. What is the meaning of soft dielectric breakdown? You have created a controllable filament. Controllable filament is that which can be turned on and off. If you don't stop your forming process at this particular compliance current, you are in for some trouble. Because what will happen is, if you allow this process to happen without stopping this process, what is the meaning of stopping this process? You set your external measurement protocol such that the moment this particular compliance current is hit, your voltage to the system is cut off. If you don't do that and you keep applying more voltage, what will happen is it will result in a hard dielectric breakdown. Hard dielectric breakdown, once the filament is formed, the filament is so thick or so big that you will not be able to switch it back again. You will not be able to turn the filament back again. So it is a one permanent damage. So that is not very useful for RRAM devices. And this is why you use compliance current for inducing soft dielectric breakdown. I hope this makes sense. Any questions from the online audience?
Sir,
Yes, please.
yes, sir. So during SRAM operations, when we are studying, like if we are calculating margins for read and write, so we saw that at different corner configurations, like for FS or SF or FS global or SF global. So generally, we see that the trend is like that the read margin is worst at I would say FS, or and the write margin is at SF. So, what should be the difference? My means it should be worst at FS or FS global, or similarly for the right, it should be SF or SF global. What should be the difference, like FS and FSG corner process?
Okay, so I think you are using terminology which is not universal. But first and foremost, just you said that we used to calculate margins. The noise margins are not calculated for write. For write, noise margins don't make any sense. So we generally calculate hold noise margins and read noise margins. And these hold noise margins and read noise margins, at least for our codes, we have restricted to the static noise margins only. Now, coming to your question, which corner cases are you mentioning? What is this FG?
So the if I explain my terminology, that is means that if I say FS, that means the NMOS is in the fast state and the PMOS is in the slow state. So VT wise means the NMOS VT would be less because it is in the faster state, and PMOS in the slower state because VT would be high.
So in fabrication, what happens is you have these FS, SF corners. Due to fabrication variabilities, the threshold voltages will be different. So if you have a higher threshold voltage, it will be lower. It will be a slower system. So that is what he's referring.
Acha, okay, no. So I understand what you're saying. FS. Okay. So you mean the threshold voltage of a okay, I get the question.
Changes, yeah. VT changes.
Let's VT. Yeah, you can just say VT.
Yeah, VT.
Understand. Yeah, thank you. So of course, so as you can see, let's look at it from first principles. So you have, what does noise margin really depend on? The noise margin, as we saw, depends on the maximum size. So we will just stick to, for the time being, for static noise margins. So what does the noise margin indeed depend on? It depends on the maximum square that you can fit inside the smallest of the loops, right? That is what we kept seeing.
Yeah.
And this was the formulation to calculate that. You kind of tilt it by 45 degrees and keep calculating a difference. And you try to see the smaller of the loops which you can fit in. And as you are rightly saying, the idea generally is to have an ideal balanced inverter, right? Idea is that you should have an ideal and balanced inverter. What is the meaning of ideal balanced inverter? That the strengths of both the NMOS and PMOS are ideally the same. But if as we have shown over here, you are asking the same question in a different terminology. If the NMOS is stronger, that's what you mean, right? If an NMOS is stronger or a PMOS is stronger, your inverter balance will just tilt away. And then you have to see, because of, for example, here, if the NMOS is stronger, you will see this will be the red line, will be the transition in the VTC characteristic. If the PMOS is stronger, it will be something else. So any disbalance in your inverter configuration which comes from your process variations. So FS and whatever you're mentioning is just different process corners. It will adversely affect your static noise margins. How do you calculate it? But so the key way to calculate it, I think we don't have the graph. Okay, so what people generally do is they do not do these hysteretic loops, as you can see in this particular graph, for just one. Just they don't do it for one SRAM cell. They keep repeating these hysteretic loops for many SRAM cells. So if you go to Google and search, you will see that there is this whole bunch of curves that come across. And in that bunch of curves, where you account for different device to device variability, and then they try to calculate what is the smallest. If still you see some window of daylight in the smallest hysteresis loop, you say that this is a workable SRAM cell. Does that answer your question? How are these FS and SF will change the strength of the NMOS and PMOS, which will change the balance of the inverter, and therefore it will shrink the sizes of the hysteretic loops, and that will also change your at least read noise margins and hold noise margin. Does that answer your question?
Yeah, somewhat. But just one more counter question. Like, if in a cell we are making NMOS stronger, so that means that we are making our excess transistor also stronger. So there will be a trade-off
No,
between
no.
that.
I think we should stop here. There are different things. So the operational, what is operational? Okay, I think we should go back to our So there is no guarantee. So you're talking about process variations. So we will not confuse two things. One is process variations and intentional sizing. Okay. So in intentional sizing, you make sure, let me go to the correct diagram. For intentional sizing, you make sure that the PD1 transistor is stronger than the PG1 transistor. But this does not account for regular process variations. The simple, when you make PD1 transistor stronger than PG1 transistor, you just make the width a little bit more than PG1. Rough
That is
value.
on the basis of sizing, not on the basis of VT.
Yes, absolutely. But what you are saying is, so a best way to explain is on an average, the pull down transistor, if the cell ratio is 2, on an average, the pull down transistor on an average will be 2 times stronger than the pass gate transistor. But due to process variations, there will be a mean and standard deviation. And that is what you account for.
Yes. Okay. Yeah.
Does that answer your question?
Yes. Yes. Sure. Sir. Thanks.
Well, please feel free if you have some other questions to ask. Okay, we'll wait for 5 more minutes and then.
Sir, just a general query related to examination. I will be first time appearing for a NPTEL examination. So is it a means objective type of exam or a subjective examination?
It is objective.
It is an objective
Yeah.
examination. So there will be, but there may be some numericals where we need some calculations. Sir.
Yes.
So that could be, I can consider that as a gate pattern almost. So.
Yes. Similar. I'm not familiar with what the latest
Ah,
gate pattern is, but
okay.
it will be MCQs. Yeah.
Not NAT.
Sorry?
Like numerical answer type.
I don't think so. No. It's just multiple choice questions, MCQs.
Okay.
I'm just talking about our course. I don't take it
Yeah.
all of NPTEL. Yeah.
Yeah.
Which are you studying or are you working?
Actually, I'm working in the industry
Okay. Where are you working?
right now. Qualcomm.
Oh, okay. Very nice. So, Saurav, since you are interacting, are you able to follow the course and does?
Yes, sir. I have studied according to my pace till NAND flash. Neuromorphic and just I have to study. Yeah, I have followed till NAND flash, like from starting from the beginning from SRAM and then DRAM, MRAMs. Following.
Okay, you are able to follow.
Yeah, I
Okay.
have bit knowledge on like this, working on SRAMs and these things in the industry as well. So it was good to see it from the beginning, from the scratch, that how it is working. So it is helpful. Yes.
Okay, great. Thank you. I think if we don't have any questions from anybody in online audience, we have exhausted the questions on the discussion forum also. So I think we can close the session now. Yeah.
Sir, there is this PDF that you are using. It is a merged one. Actually, we are
Yeah.
getting the week wise.
Yeah.
So when we upload this merged one as well, that would be helpful because seeing it in one go, maybe we can see.
So you can download all the PDFs which are there and you can use a software to merge it, right? So I do not have rights to distribute. The NPTEL does that, as you know, you have to put the logo. We have discussed many times. I mean, yeah, I don't have the rights to just freely distribute the. You
Got
can
it.
download the 12 and you can just so many software
Right.
available online.
Sure.
Yeah. Oh, I think there are some questions. If I don't know, chat. Abhishek is asking, sir, when are you going to teach compute in memory? It's there in the schedule. Compute in memory is in week 12. What? Oh, what are you going to? Yeah, that's suspense. Let's wait for week 12. We are going to talk about what is I think a lot of interest in compute in memory. Good. So we are going to go over the details of why do you need compute in memory? What can compute in memory do, which spiking neural networks do not do? What are the advantages of compute in memory? What are the two different kinds of compute in memory? We will look at digital and analog in memory computing. What is the first generation of computer memory, which is near in memory computing? And maybe just a month later, you will come to know 3 weeks later, you will come to know all the topics. And then what is digital in memory computing? How digital in memory computing does Boolean algebra inside memory by changing the peripherals and by changing how you do the pulsing sequences. And then in analog in memory computing, how you can accelerate vector matrix multiplications. And from this current time, you will see what is so important about vector matrix multiplication. Is the fundamental computational bottleneck, or maybe most heavy computational element in neural networks. Yeah. Oh, you already answered. I didn't see you. Okay. Thanks, Rupak. Yeah. Good to see that a lot of interest in compute in memory. Very nice. Okay, if there are no more questions on the chat or somewhere else, maybe we can. So, NPTEL guys, is there any question? I can see another. Yeah. Yes, we will discuss some of it. So our friends from NPTEL, are there any other questions in some other forum, or can we close the session? Is there a question? So we will discuss this. So Abhishek, just few more weeks, we will discuss which one is used. It's, as I said, digital in memory computing and analog in memory computing does entirely different things. So they are used in different places. So digital in memory computing just does Boolean logic operations, whereas analog in memory computing does acceleration of vector matrix multiplication. So mostly is probably not the right way to approach the question. They are used for different contexts. That would be a more fair answer, to be honest. Oh, so, okay. People can access the chat without appearing. I don't see. Okay, no, never mind. Okay, I think if there are no questions, we can probably close here.
Okay, sir. Yeah. Thank you for the session.
Thank you, everybody.
Thank you, sir.
Thank you. Thanks a lot. Thanks for coming.
Thank
Bye.
you, sir.
Thank you.